Look up at the night sky. What do you see? Is it just a canvas of darkness dotted with tiny lights? Or is there something more profound hidden in that vast expanse? Stars scattered across the vast expanse of space, each one a distant sun, a beacon of light in the infinite darkness, holding secrets that have fascinated humanity for millennia. These twinkling points of light hold clues to the universe's grand design. They are not just distant suns, but cosmic storytellers, narrating the tale of creation, evolution, and the very fabric of reality. But have you ever wondered what those stars are made of? What elements compose these celestial bodies that shine so brightly in the night sky? What are the fundamental building blocks of reality itself? From the smallest particles to the grandest galaxies, what constitutes the essence of everything we see and know? These are questions that have captivated humanity for centuries. Philosophers, scientists, and dreamers alike have pondered these mysteries, seeking to understand our place in the cosmos. For millennia, we believed that the universe was deterministic, predictable, like clockwork. The celestial bodies moved in precise orbits, and the laws of physics seemed unchanging and absolute. We assumed that if we knew the initial conditions of every object, we could predict their future with certainty. The universe was a grand machine, and we were beginning to understand its gears and cogs. But then, at the dawn of the 20th century, a revolution occurred, a paradigm shift that would forever change our understanding of the cosmos. Scientists peered deep inside the atom, and what they found shattered our classical understanding of the universe. The atom, once thought to be the smallest indivisible unit of matter, revealed a complex and dynamic inner world. This revolution gave birth to a new field of physics, quantum mechanics, a field that challenged our notions of reality and introduced concepts that were both baffling and beautiful. It unveiled a world stranger and more wondrous than we could have ever imagined. A world where particles could exist in multiple states at once, and where the act of observation could alter the outcome of events. A world where the very fabric of reality is woven from uncertainty and paradox. Where particles can be entangled across vast distances, and where the boundaries between past, present, and future blur. This is the story of that revolution. A story that takes us from the macroscopic world of everyday experience to the microscopic realm of quantum phenomena. A journey into the heart of matter, where the rules of the everyday world cease to apply, where the familiar laws of physics give way to a new and mysterious set of principles. This is the story of quantum mechanics, a tale of discovery, wonder, and the relentless human quest to understand the universe. Join us as we explore the mysteries of the quantum world and uncover the secrets that lie at the heart of reality itself. Quantum mechanics is the study of the very small. It's a branch of physics that explores the behavior of matter and energy at the atomic and subatomic levels. And it's a world that operates by a very different set of rules than the ones we experience in our everyday lives. In the quantum realm, things aren't so clear-cut. Particles can be in multiple states at once. They can exist in a haze of probability, their properties not fully determined until we observe them. It's a world where the act of observation itself can influence the outcome of an experiment. This might sound strange, even impossible, but the predictions of quantum mechanics have been verified time and again through countless experiments. It's one of the most successful scientific theories ever developed, and it underpins much of our modern technology. So, buckle up as we dive into this strange and wonderful world. Let's explore the fundamental building blocks of the universe and uncover the secrets of the quantum realm. Imagine shrinking down to the size of an atom. Picture yourself in a world so small that the very fabric of reality seems to change. You'd find yourself in a miniature solar system with a dense nucleus at the center, much like the sun in our solar system. This nucleus is incredibly tiny, yet it contains nearly all the mass of the atom. Surrounding this nucleus are even tinier particles called electrons, which move so quickly that they create a sort of cloud around the nucleus. The nucleus itself is made up of protons and neutrons, which are held together by a powerful force known as the strong nuclear force. These protons and neutrons are not fundamental particles. They are composed of even smaller particles called quarks, bound together by particles known as gluons. But here's where things get weird. The behavior of these particles doesn't follow the rules of classical physics. Electrons don't orbit the nucleus like planets around a star. Instead, they exist in a cloud of probability, described by what's called a wave function. This wave function is a mathematical description that doesn't tell us exactly where an electron is, but rather gives us the probability of finding it in a particular location at any given time. Imagine trying to locate a specific electron. The wave function provides a map of probabilities, showing where the electron is likely to be found, but never giving a precise location. Think of it like a fan blade spinning really fast. When the fan is on, you can't pinpoint the exact location of the blade at any given moment. Instead, you see a blur, a probability distribution of where the blade might be. This blur is similar to the electron cloud around the nucleus. The blur represents the areas where the electron is most likely to be found, but it doesn't give a definite position. That's kind of what it's like with electrons. They exist in a state of uncertainty, never in one fixed place until we observe them. This inherent uncertainty is a fundamental principle of quantum mechanics, known as the Heisenberg uncertainty principle. It's not that we just don't have the tools to precisely measure an electron's position and momentum. The very nature of these particles means that their position and momentum are not fully defined until we make a measurement. This means that the act of measurement itself affects the properties of the electron. In other words, the more precisely we try to measure one property, like position, the less precisely we can know another property, like momentum. This strange behavior isn't just limited to electrons. Other subatomic particles exhibit similar properties, leading to phenomena like quantum entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of another, no matter the distance between them. These principles form the basis of quantum field theory, which describes how particles interact and how forces like electromagnetism and gravity operate at the quantum level. Scientists use particle accelerators to study these interactions, smashing particles together at high speeds to observe the fundamental components of matter. Discoveries like the Higgs boson have expanded our understanding of the universe, revealing the mechanisms that give particles their mass. The implications of quantum mechanics are vast, influencing fields from cryptography to computing, and opening up new possibilities for technology and our understanding of reality itself. As we continue to explore the quantum realm, we uncover more about the fundamental nature of the universe, from the smallest particles to the vast expanse of space. The journey into the world of atoms and their elusive inhabitants is a testament to human curiosity and our relentless pursuit of knowledge. Who knows what future discoveries await us as we delve deeper into the mysteries of the quantum world? This brings us to one of the most mind-bending concepts in quantum mechanics, superposition. It states that a particle can exist in multiple states simultaneously until it's measured. Imagine a particle that can be in two places at once, or spinning in two different directions at the same time. This is not just theoretical, it has been demonstrated in numerous experiments. It's like a coin spinning in the air. It's neither heads nor tails until it lands. But in the quantum world, the coin can be both heads and tails at the same time until we look at it. This duality is what makes quantum mechanics so fascinating and perplexing. The most famous illustration of superposition is Schrödinger's cat. This thought experiment, proposed by physicist Erwin Schrödinger, is designed to show the paradoxes of quantum mechanics. This thought experiment imagines a cat trapped in a box with a device that has a 50% chance of releasing a lethal poison. The device is triggered by the decay of a radioactive atom, which is a random event. Until we open the box, the cat is both alive and dead, existing in a superposition of states. This means that the cat's fate is intertwined with the quantum event, and it remains unresolved until an observation is made. Now, obviously, a cat can't be both alive and dead at the same time. This paradox is meant to illustrate the counterintuitive nature of quantum mechanics. This thought experiment is meant to highlight the strangeness of quantum mechanics and how it differs from our everyday experience. In our macroscopic world, things are either one way or another, but in the quantum realm, they can be in multiple states at once. In the quantum world, particles exist in this nebulous state of superposition until we force them to choose a definite state through measurement. This act of measurement is what collapses the superposition into a single outcome. It's as if reality itself is constantly in flux, with possibilities collapsing into actuality only when we observe them. This concept challenges our understanding of reality and forces us to reconsider the nature of existence. Scientists around the world are conducting experiments to better understand these phenomena. They use sophisticated equipment to observe particles at the quantum level, trying to unlock the secrets of the universe. Another fascinating aspect of quantum mechanics is entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of another, no matter the distance between them. This spooky action at a distance, as Einstein called it, suggests that information can be transmitted faster than the speed of light, defying classical physics. These principles are not just theoretical, they have practical applications. Quantum computing, for instance, leverages superposition and entanglement to perform calculations at speeds unimaginable with classical computers. The future possibilities with quantum technology are vast, from revolutionizing computing to enhancing encryption and even advancing our understanding of the universe itself. As we continue to explore these quantum mysteries, we are reminded of the vastness of the unknown and the endless potential for discovery. Embracing the uncertain is not just a scientific endeavor, it's a journey into the very fabric of reality. Prepare to have your mind truly boggled because we're about to explore another bizarre phenomenon of the quantum world: entanglement. Imagine two particles that are linked in such a way that even when separated by vast distances, they remain connected. Measuring the state of one particle instantly determines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, seems to violate the very fabric of space-time. It suggests that information can travel faster than the speed of light, which contradicts our current understanding of physics. Entanglement is one of the most perplexing aspects of quantum mechanics, and it has profound implications for our understanding of the universe. It suggests a level of interconnectedness that challenges our classical intuitions and opens up exciting possibilities for future technologies.